start the last. I think we finished with the lecture, so we'll do the last tutorial for this course, which is related to finite state machines and counters. Right. We start with the first question. So we give you here a problem. We say draw the state diagram for a Moore machine to implement the following. So we give you a description of a problem, and we want the first thing to do to draw the state diagram for this problem. So from here, you need to tell me how many states do we have. So we will have a circuit. We are talking about state diagram. So we will have a circuit that will have inputs. It will have output. It will have definitely clock here because we will need to use flip-flops. So you need to tell me what are the inputs, the outputs. This is the first thing that we need to identify. How many outputs do we have, and what are the possible states for the outputs or the possible values that we can have. And then based on this, we draw the state diagram, and then we do the rest, the excitation table. And so the first task is the state diagram. So what does it say, the first line? I mean, when you read this problem, so what do you think? How many inputs do we have? We don't talk about the clock, yeah? Clock is already there. It's a sequential circuit. So what are the other inputs that we have?
We have the X.
Good. So as you can see here, we are talking about a control input X. So we have X is one of the inputs. What's X? I think that's it. So this is and based on this X, we will have different values for the output. We say while control input X is 0, output to alternate between state 0 and 3. So I know that I have state 0, and I know that I have state 3. So those are the possible states. And then, if control input X is equal 1, while in state 0 or 3, go to state 1. So I know that I have state 1 as well. While control input X is equal 1, output to alternate between state 1 and 2. So I have 2 as well. If control input X is 0, while in states 1 or 2, go to state 0. So we need to go to state. So that says those are the possible states. So we have 0, 1, 2, and 3. So the highest state is 3, which means what is 3 in binary is 1, 1. This means I need an output with 2 bits. This is the output. So all this information, we got it from here. Now we need to draw the state diagram and show the transition between state and the order. So I will switch to whiteboard to draw the state diagram. I hope you can have in front of you the questions as well. So the first point, it stays here, while, so we know that we have 4 states. 1, 2, 3, 4. So we have 4 states. We say the first point, it says while control input X equals 0, output to alternate between states 0 and 1. So we have state 0. If I put 0, 0 here, 1, 1 here. Also, yes, 0 and 3. While control input X is 0, outputs to alternate between states 0 and 3. Alternate, which means if I am in 0, I go to 1 or to 3. If I am in 3, I go to 0. So this is from the first line. Let's do one here for the clarity of the drawing. If I do 1, 1 here, this is state 3. So state 0, state 3. If I call this state 1, and this is state 2. So those are the states. Again, I will repeat the first point. It says while control input x is 0, output to alternate between states 0 and 3. So it goes, if x is 0, if I am in 0 and x is 0, I'll go to 1. If I am on 1 and x is 0, I go to 0. So it alternates between the two. This is from the first point. Second point, if control input x is equal 1, while in states 0 or 3, go to state 1. So if I am in state 0 and the control line is 1, I go to, I'm in state 0, I go to state 1. This is if x is equal 1. And it says as well, while in state 3 and x is 1, I go to, again, state 1. X is 1. Third point, while control input x is 1, output should alternate between states 1 and 2. So now we have state 1 and 2. If I am in state 1 and x is 1, I go to state 2. If I am in state 2 and x is 1, I go to state 1. So it alternates between them. It stays here. So this is what we will have. And by the way, I can do this by a bidirectional arrow. X is equal 1. So I can do 2 arrows like I did here, or I can do a bidirectional arrow. So if I am in state 1 and x is 1, I go to state 2. If I am in state 2 and x is 1, I go to state 1. And then it stays here, 1, 2, 1, 2. So the system should keep doing 1, 2, 1, 2 if the x is 1. Right. For x is, yeah, if x is 1. Last point, it stays, it states, yes, if control input x is 0, while in states 1 or 2, go to state 0. So if I am in 1 and x is 0, I go to state 0. X is equal 1. 0. And if I am in state 2, and again x is 0, I go to state 1. That's it. So this is the state diagram from the description that we have in this problem, in this question. Is this clear? So the next step is, next question is to obtain minimal excitation logic functions for your system. We draw first the excitation table, and then we find the logic. So again, we say we have, so remember, we have a circuit that has one input, x, the output is 2 bits, and then of course we will have clock, and here I know in advance that I need to flip-flop because the output is 2 bits. Now we need to draw the excitation table. So what do we need to find? We need to find D0 as a function of Q0, Q1, and X. And I need to find D1 as a function of Q0, Q1, and X. Of course, when I say Q0, Q1, I may have Q0 bar, Q1 bar as well. As well as for X, I can have X bar as well. Yeah, so it's X. So I need to draw the excitation tables. In this case, I will have X, Q1, Q0, and then I will have, let me leave some space here for the current states, D1, D0. And then I will have the possible combination 0, 1, 0, 1, 0, 1, 0, 1, 2 zeros, 2 ones, 2 zeros, 2 ones, and then 4 zeros, 4 ones. Right. I will put here next state. You don't have to do this, but it can help you to. So which means for Q0 and Q0 and Q1. So what will be the next Q0 and Q1 if I have? So what does this mean here? If I am here, it means I am in state 0, 0, which is state 0, right? I will put the number of states here. So state 0, state 1, state 2, state 3. And this is state 1, 0 again, state 1, state 2, state 3, right? But of course the x will change. Here we have x. For the above 4, x is 0, and for the cases below, it's 1. All right, so we start with the first one, and then I will just follow the state diagram. So what should we have here as next state for the first case? If I have 0, 0, and x is 0, what should be next?
1, 1.
So we are here, and x is 0. So we should get 1, 1 here. Good. And then next one, if I am in 1, which means I am here, and x is 0, what should we go? Next.
0,
0,
0.
0, 0. Good. And I will keep doing this. Now, next one. If I am in 2, which means I am here, and x is 0, I will go to 0, 0 as well. State 3, I am here, and x is 0. I will go to 0, 0 as well. Right? I'm just following the this state diagram. Now I will go to, again, state 0. I will have again here state 0, but x is 1. So state 0, x is 1. Where should we go? We go to state 1, right? X is 1, and x is 1. So the state is 1, and x is 1. Where should we go? 2, right? We are here. State is 1, x is 1, so we go to 2. Next, state is 2, and x is 1. So we are here, and x is 1. Where should we go? We go to 1. We are lost 1. X is 1, 1. Oh, sorry, state is 1, and x is 1. Where should we go? We go to 1, state 1. And that's it. So I'm done with the next state. So now I need to answer the question, okay, what should I do on D0 and D1 to get what I want next? Because this is the flip-flop, Q follows D. So whatever I have here, all this, I will just take it and put it here. Right? Because if I want to get 1, 1 next, I will just put 1, 1 on D0, D1, and so on. So the flip-flop is straightforward. Right? If I know what are the next states, so the D's should be equal to the Q's for next state. And then that's it. Next time, what do I need to do next is to find those expressions. Of course, I need to use I can use K-map here, or I can work with the expressions. So if I use K-map, zero, 0, 0, 1, 1, 0, oh, sorry, 1, 1, 1, 0. Gray code. Then 0, 1. What should I put here?
X and Q1.
X and Q1. Excellent. So X, Q1. And you need to be careful. If you do a mistake here, then that's it. If you put Q0, Q1, then it's wrong. So you follow this, X and Q1, what we used to do in and then here is Q0. Right. And then, so this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. I will just fill the table. Of course, I need to do two, one for D0. So if we start with D0, and then one for D1, right? So 1, where do we have 1? We have it in 0, 1, 2, 3, 4, 4, and then 6 and 7. The rest are zeros. How many groups can I get here?
3 groups of 2.
How many groups?
3
Say again?
groups of 2. 3 groups of 2.
3 groups of 2, you will not get the best logic.
No, yeah, sorry, 2 groups of 2.
You just need 2 groups of 2, right? So I just do this group, and I will do this group, and that's it. I'm done with all the ones that I have. So this one is what?
X,
Q
Q1.
here,
X and Q1.
X and Q1. That's it. Good. And then this one is Q0 bar, Q1 bar, which means D0 is equal to X dot Q1 plus Q0 bar dot Q1 bar. And that's it. So this is for D0. Then I need to do the same for D1. D1, if I try to use the same table here, so what do we have for D1? So we have, as you can see for D1, it will not help because we will have 1 here, and the other one is 0, 1, 2, 3, 4, 5 in 5, and the other one here. So we'll have those 2 ones. So I cannot do groups. So D0, D1 is equal, we just get it from the truth table, or the groups with a single one. It's basically it's X bar dot Q1 bar dot Q0 bar plus X dot Q bar dot Q0. So this is the expression for D1, and I can simplify it further. Of course, I'm not going to waste my time here. We'll just show you the solution, and then of course we can find the. So this is the expression that we wrote, the last one. And then of course you can simplify it further by just taking Q1 as a common factor, and then you will get it's equal to Q1 bar by Q0 XOR X NOR X. So this is an X NOR. And then the rest is just drawing the circuit. So I know that I have 2 flip-flops. And then this is the expression. This is what we found for D1. And these are the gates that we found for, this is for D1 and this is for D2. Is this clear? I'm just following the expressions that we've got, and that's it, to connect D1 and D0. So this is the main task, is to find the excitation logic to get what we want next. And here you can see the final output is we get it from Q0 and Q1. And as you can see here, for both flip-flops, we are using the bars, Q0 bar and Q1 bar. And then this is the circuit. We have X and clock as input, and output is the 2 bits from Q0 and Q1. Right. Is this clear? Before we move to the next question. Next question. What we want to do is to design a synchronous binary counter which will increment up to 7 and then return to 0. I think we did a counter in the lecture 0 to 3, right? That counts from 0 to 3. So which means we use D0 and D1 and we got D0 and D1. Here we want a counter that counts up to 7. Up to 7, this means I need 3 bits, which means I need 3 flip-flops. So which means I will have D0, D1 and D2. So I will have 3 instead of 2. But the rest is exactly the same. So I don't want to spend time here. And then we ask you to sketch the circuit, of course, by finding first the excitation logic, and then you use a one-level MUX implementation. If I switch to the solution, so which is very similar to what we did before. Of course, here we said it's just a simple counter. There is no need for, the state diagram. Of course, if you want to draw the state diagram, you just need to have 7 circles, and then there is no condition in a transition. Every clock cycle, we go from one state to another. So this is the state diagram. Of course, we need here, as I said, 3 flip-flops. So we have D0, D1, D2. And then I just put the current state here in decimal. I put the values in decimal. Of course, you can put them in binary. So if it's 0, next is 1. If it's 1, next is 2. If it's 2, next is 3. If it's 3, next is 4. Until 7. If it's 7, next is 0. And those are the possible combinations. And then again, what we have here is the binary representation of those. So it's 1, 2, 3, 4, 5, 6, 7, and then 0. So it's just basically the binary representation. The next Q, the binary value for the Qs should be equal to D. And then we just did the K-maps. So we found that D0 is Q0 bar, so there is no need for any gate. D1, so this is for D0, this is for D1. D1 is just an XOR gate between Q0 and Q1. And then the last one, D2, is more complex, but this is what we got from the K-map. And then I managed to simplify it further to have it just an AND gate and an XOR gate. By observing, you should know that you can simplify further. Simplifying, I'm not keeping it as a sum of product. I'm changing, so I'm using the XOR gate. Yeah. And then, is this clear? Yeah, I think it's very simple. I mean, we just added one input, and then the rest is just to draw the circuit. Is this clear? Then next, we ask you to use one-level implementation. So for D0 bar, it's already Q0 bar. There is no need for any multiplexer. For this one, D1, we can replace this multiplexer, and for D2, we can replace this one as well. If we take a one-level implementation, so this is basically what we are doing here, yeah? So if I can just split this. So I need to find first, we said D0 there is no gate, so it's just a wire. There is no need for D0. I just need to do D1 as a function of Q0. And I need to do then D2 as a function of, sorry, this is for 2-level implementation. The question was for just 1 level, which is basically we just take this one. This will be the inputs to the multiplexer, right? For D1. This is what I put here. And then this Q0 control lines are Q0, Q1, and Q2. And the same for D2. So this will be the For D2, this will be the inputs of the multiplexer. This is for one-level implementation. Now, if we ask you two-level implementation, which I didn't put this question, but we can do it here quickly, which I already started here. So if I do, I don't need D1, because as I said, D1 is just a wire connecting Q0 bar. So what is D1 as a function of Q0? So 0, 1, I get 0, 1, so it's Q0. 0, 1, I get 1, 0 here, it's Q0 bar. And then 0, 1, I get 0, 1, it's Q0. And then 0, 1, I get 0, 1, so it's Q0 bar. And I have the Q0s and Q0 bar, right? So I can just take them from the... So if I want to draw the multiplexer, I will have 2, 2, 1 in my circuit. So this goes to D1, right? And then here, I will have the 4 inputs. So those two will be connected to... I'm not putting the full circuit, yeah? So those two will be connected to Q0. And the remaining two will be connected to Q0 bar, right? And then I will have here, what should we have here? This control lines. This is 4 to 1, not 2 to 1. So what do we have here? What do we have in the two control lines?
D2 and D1.
No. I think you are lost, yeah? It looks like you are lost. What are the outputs here? What are the inputs here for this, if I consider this as a truth table?
Q0, Q1, and Q2.
Yes, Q0, Q1, and Q2. So what are the outputs? Is D1
Q2 and Q1.
Yes, so it should be Q1 and Q2 here, right? So this is what we should have for the control line. It's just what we did before when we have A, B, C, right? So if I have A, B, C, and then I will have X as the input. Now if I look for what is X as a function of C, sorry. This is what we did in the past, yeah? 0, 0, 0, 0, 0, 1, 0, 1, 0, 1. Or zeros, or ones. And then we split, we try to find what is X as a function of C. So let's say we will get here C, C bar, C, and C bar. And then when I draw the multiplexer, it's a 4 to 1. I will have C, C bar, C, C bar, and then I will have X, and here it's A and B, right? And we did this, yeah? I'm just applying what we have done in here. So if we ask you to replace, so D1, we found D1, and we did the implementation using gates. We ask you to replace the gates with a multiplexer. So we did one level implementation. One level is very easy. We just take those values as they are, and those will be the inputs of the multiplexer. And then the other control lines will be the Q0, Q1, and Q2. Added the question, we said if we do the one level implementation, a two level implementation, we found out that we will get Q0, Q0 bar, Q0, Q0 bar, and those will be here, the inputs of my 4 to 1 multiplexer, and then the rest is Q1 and Q2. And we are not talking about D2 yet. Now I will move to D2. I'm done with D1. I will move to D2, and I will find as well what is D2 as a function of Q0. So what is D2 as a function of Q0? So it's 0, 1, I will get 0 here. 0, 1, I will get 0, 1, so it's Q0. 0, 1, I will get 1, 1, so it's 1. And then 0, 1, I will get 1, 0, so it's Q0 bar. And then I will draw another multiplexer here for, so I will have D2 here, 4 to 1, 0, Q0, 1, Q0 bar. I'm not putting this in the full circuit, but if you have a question like this, you need to show the full circuit. And then again, I will have Q1 here and Q2, just connections. And you know from where you get them, yeah? Q1, Q2, Q0, Q0 bar, they are from the flip-flops. So those two multiplexers here can replace those two here. And then you just do the connections. Is this clear?
Yeah.
Okay, good. So this is for the second question. Third question. Design a mod n modulo n. Mod n means a modulo n counter that will execute the numerical sequence 0, 1, 3 repetitively. You should direct any unwanted state into wanted states that give the simplest logic functions. And then we ask you to sketch the circuit diagram. Right, so what we want to do here is 0, 1, 3. And repeat 0, 1, 3. So we don't have 2. 2 is an unwanted state, but we need to consider it in our design, as I showed you in the previous example in the lecture. So we have 3 states. So how many flip-flops do we need here?
2.
We need 2. Why we need 2?
Because the most bit is 3, which is 1, 1, which is 2 bits.
The highest state is 3, which requires 2 bits, right? It requires 2 bits, 1, 1. If you put 3, let's say I will use 3 states or 3 flip-flops. Of course, it's correct, but you'll be wasting your time or your resources, because for the last output, it will always be 0. So the last flip-flop, we know in advance that it always gives you 0. But there is no point to do this, right? So we have 3 states, 0. In such examples, there is no need to draw this state diagram, right? And then we go to 1, and then we go to 3. There are no conditions. Every clock cycle, if you are in 0, you go to 1. If you are in 1, you go to 3. If you are in 3, you go to 0. And that's it. And then next, we need to draw the state diagram. And then from the state diagram, we need to identify the, or to find the excitation logic, right? So if I draw the, let's switch to the whiteboard, it's better. State diagram. So you said we need 2 state or 2 flip-flops. So we have Q0, Q1, and of course we will have D0 and D1. Current state. Next. Sorry, I need space here. Next state. So for Q0, Q1. Right. So current state 0. Sorry. This is the current state, by the way, yeah. So 0, 0, 0, 1, 1, 0, 1, 1. So those are the possible states. So if I am in 0, 0, what should be next? First case, if I am in 0, 0, what should be next state?
0, 1.
0, 1. Yeah, so this is what we want to do. Yeah, 0, 1, 3. So it should be 0, 1. If I am in 2, this is invalid state, right? I'll just put x here. This is invalid, but I need to redirect it to a valid state. So for now, I put x because I don't know, right? Which means I need to put x here. If it's 1, 0, oh sorry, 1, 1, we go to 3. It's not the this is the state. It's valid. 1 is valid state, and nobody mentioned anything. So this is state 2, invalid. So 0, 1, which is this one, 1, we go to 3. And then, if we are in 2, this is invalid. If we are in 3, we go to 0. And then we just copy those here, as I told you, x, 0, 0. And then I need to guess D0. I need to redirect this x should not be equal 1, 0, because this is 2. So I have to be careful. X should not be equal to 0, 1, which is 2. I cannot redirect an invalid state to invalid state. So I should redirect it to a valid state. So I need to consider this when I do the K-map, right? So we have 0, 1, 0, 1. So Q0, or is it Q1, Q0? 0, 0, 0, 1, 2, 3. Right? So if I start with D0, so what do we have? We have 1, 1, and then we have what? X, and then 0, right? Do you follow? Yeah. So what should be the best value for here for X? To get the best
0.
value. Huh? 0.
0.
Okay, good. So if I put 0 here, I should get just one group here, right? Which gives me D0 is equal to what? Q1 bar, right? There is no gate. So it's just a wire, which is good. So by putting 0 here, so which means in this first X, I put it 0. The next X has to be 0. I cannot put 1. If I selected 0 here, in this case, then do you understand? Yeah. The next X for D1 cannot be 0, cannot be 1. It has to be 0. If I put 1, I will be redirecting to the invalid state. And then, so I can repeat this for Q1, Q0 for D1. So I will get 0, 1, X, and 0, right? Zero, 1, X, and 0. So this has to be 0. Which means D1 is equal what? I have just one here. It's equal to Q1. Sorry, Q0.
Q1 bar or Q0?
Yeah. Q0 dot Q1 bar. So this is D1. And then I will just draw just an AND gate, basically. For both, I have just an AND gate, which is fine. So if I switch to the solution, And that's it. So D0 is equal to Q1 bar and D1 is equal to Q0 dot Q1 bar, which is an AND gate because I already have the Q1 bar. I already have the Q0 bar. So Q0 bar is not used here in this case, in this example. Right. Question we have. Yeah, we ask you as well to do this with the MUX. I think it's very simple as well. So you need to replace the X with the state that we need. Here in my solution, I just put initially 0. Yeah, but what I did in the whiteboard is better. Here, because I know in advance that I should use the you know, I will get 0, 0 for the best solution. But what I did on the whiteboard is what you should do. Put X first, and then you guess the best one. And the best one in this example is 0, 0. And then you get the one level implementation, which basically I need to do it for just D1. So one level, so D1. I just get those. Those will be the inputs that goes to the multiplexer. And you should know how to do the two-level implementation as well by splitting this into 2, and you get D1 as a, and you use a 2-1 plexer instead. I didn't put the question, but I think you can do it as well. Next is question 4. We'll jump to question 5 because it's similar to this question, but we ask you to use so we'll jump to question 5 and then I will come back to question 4. We want to do the same problem, this one, with a JK flip-flop. Of course, knowing the excitation table for a JK flip-flop. So we'll jump to question 5. So I want to do the same problem with using JK flip-flops. So counting from 0 to 1, sorry, 0, 1, 3. So 2 is invalid. As you can see here, I put 2 as the last one, but it's fine if you put it here. It doesn't matter as long as you know what is the invalid one. So it doesn't matter. You can put them in order, but you highlight the invalid one and make sure you use X's there. Right. Here, to do the solution, I put X. And then I have, as you know, I'm going to use JK flip-flops. For each one, I will have J0, K0, and then J1, K1. So I will have 4 outputs now. It's not just 2 like the D0 and D1. Inputs, which are the J0 and K0, and then J1 and K1. And then, of course, the rest I will just here to guess this content, the zeros and ones. I will just follow the excitation table for the JK flip-flop, going one by one. So we'll do Q0 first. So the current value for Q0 is 0, and I want the next one to be 1. Then for this, I need J and K to be 1x. So it could be 1, 0 or 1, 1 to get what I want. And I do all possible inputs for Q0, and then I will move to Q1 and then get the possible values for J and K as well. And then that's it. So this is how we get the table. Right. For the invalid state, I will redirect it to X for now. So I don't know what is this. X could be 0, it could be 1, it could be 3. Right? Here. So I can have 0, 1, or 3, but not 2. And I just put X here. So everything is X. And then I will replace those X's with values. But I have to check. You need to make sure when you replace those x's here, and then when you have 0, what should be the next value for x, for q0, and then the same for q1. When you have 1, what should be the next value? So you have to make sure you avoid this. So this x should not be equal to 1, 0 at the end. So it's the same condition that we did before. So we have to make sure that it's not 0, 1. And then based on this, I started my, this is J0, K0. So I got J0 is equal to 1. So I found out that the best value is 1. For K0, the best value is, for those x's is, and remember, we have x's here, which we don't care. For example, this x, when I start J0, for example, let's start J0. So J0, I have 1. What I put in red here, they were x's. So this was an x, this was an x, and this was an x. Okay, if you look for J0, so it was 1, x, x, x. And then I replaced those x's with all ones. 2 of the x's, I don't care about them. It could be 0, could be 1. Any one of them could be 0, could be 1. I don't care about them, right? But this one is very important. So I need to put to take a note of it. So what was it? It was 1. Because I need to check at the end to avoid the invalid state. So this one, I put it 1. Here, right? When I got J0. And then I did as well the other one for K0. For K0, I put it 1 as well. Is this one related to 2, state 2. This is 1, this is 1. I put it 1, 1. So what does it mean? It means that Q0 is 0, and we put 1, 1. This means it's a toggle. I will guess the next Q to be 1. So it's 1 here. 1, 1 will give me 1. And do you see, since this one is 1, this means I will never get 2, because 2 is 0, 1. So this first Q0 should be 0, which means it's good. I don't now for the next J1 and K1, I can put whatever I want, because it will not affect the even if it gets 0, then I will be redirecting to 1. If I get 1, I will be redirecting to 2. Oh, sorry, to 3, which means I already avoided, by just doing J0 and K0, I know that I already avoided the invalid state 2. So it's fine. So for the next ones, I don't care. I can just replace the x's with whatever I want. And then, as you can see, I will guess the best solution as J1 is equal Q0 and K1 is equal 1. I hope you get my point. Then that's it. I will just draw the state diagram. As you can see from all the expressions, I don't need any gate. It's just either connecting to 1, VCC, or just using the Q0 and Q1. And this is my circuit. Is this clear?
Exactly.
Right. Of course, with JK, as you can see, it's more complex when we design. But at the end, you will see that usually we don't use gates. We can find a good solution without the need of using extra gates. Right, I will move to solution. Question, the last one, question 4. Design the complete circuit of a mode 6 counter. I put mode 6 counter, which means it's a counter that has 6 states. 6 states, this means we go from 0. Mode 6, it means 6 states. 0, 1, 2, 3, 4, 5. We just say mode 6 counter. This means it's a counter that has 6 states and goes up 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, which means 6 and 7 are invalid. Why are invalid? How did we get 6 and 7? Because the highest state is 5. How many bits do we need to represent 5? We need 3 bits. With 3 bits, we will have up to 7, right? But those states, we are not going to use them. We need to stop at 5. So we need to design this counter. And again, we have to make sure that we redirect those invalid states to valid states. We'll switch to the solution. So we need 3 flip-flops, so you can use this equation, or you can use, as I told you, it's always good to go for the highest state. So we need 3 flip-flops. And then here again, we are going to use the flip-flops. 0, D1, D2. And again, 6 and 7 are invalid states. I just put them XX here. Again, this X should not be equal to 1, 1, 1 or 1, 1, 0. The same here, should not be equal to 1, 1, 1 or 1, 1, 0. So we need to avoid 7 and 6. But the rest is fine. I can use whatever I want. I think the state diagram, the excitation table is clear. So we start state 0, we go to state 1. State 1, we go to state 2. State 2, we go to state 3. State 3, we go to state 4. State 4, we go to state 5. And then state 5, we go to state 0. This is what we need to do, right? 0, 1, 2, 3, 4, 5, and then back. And of course, because it's a flip-flop, I can just get the binary representation for those states here. But I want next. And that's it. Now, I need to use the K-map to get the D0, D1, and D2. So if I start with D0, so what I put in red here are the states. Are the invalid states, the X's here. So starting with D0, so what does it mean here for this first X1? So this first X1, for 6, it's 1. And for 7, it's 0. So I put 1, 0 here. This gives me D0 is equal to Q0 bar. So you need to take a note of what you have used for X's. And then you check. If you find out that you are redirecting to an invalid state, then you need to redo things. Next. D1. This is for D1. This is for D0. If I go to D1 and I do the state diagram, the K-map, this is what I will get. So what do you think? I mean, 0, 0 or 1, 1 is better? Or 1, 0?
One zero would be better, but it will mean that we'll have to redirect. So
if
we'll
I
limit
put
our options.
Yeah, if I put 1, 0 here, it's better, as you said, so I can have this one as a group. But as you said, if I put here, so this means this is 1, this is 0. So it's fine so far. But again, if I go to the third one, I found out that the best ones are 1, 1. If I put 1, 1 here, so it's fine for this one, but it's not fine for the other one. So I have to choose one of them. So it's either put 0 here and keep this as it is, or I keep 1 here, but I put 0 here, and then this will change. So in both cases, I need to get one more complex than the other. So I decided here for my case, I just use 0 here and 1 in the other one. But if you choose 1 here and 0 here, it's correct. Do you get my point? Yeah, so you need to check the values that you are going to replace your x's. So as it is for this solution, I have 1, 0 here, and then I have 0, 0 here, and then I have 1, 1 here, which means here I'm redirecting to 5, and here I'm redirecting to 4, which is fine. And this is my circuit. This is my final circuit. Of course, I think this is good if we use a 2-level implementation for those, so we can replace them with 221 MUXs. 221 MUX here as well. This one is fine, it's just a wire. This is with 1-level implementation, and of course, as I told you, we can do it with 2-level implementation, where I can use just a. So if I do it here, for example, now if I need to find the 2-level implementation, I have to replace the x's, right, that we used. D0, it's fine, I don't need it. So D1, for example, as a function of Q0. So 0, 1, I will get 0, 1. So it's Q0. 0, 1, I will get 1, 0. It's Q0 bar. 0, 1, it's 0, 0. And then 0, 1 is 0, 0, 0. So for D1, I can have just a multiplexer 2 to 1, where this goes to Q0, Q0 bar. And here, both of them are 0. This is D1. And here, I will have Q1, Q2. This is for D1. For D2, as a function of Q0, I will get 0, Q0, Q0 bar, and 1. So again is another 2 to 1 multiplexer.
So aren't they 4 to 1?
Pardon?
Aren't they 4 to 1?
So I didn't. So we have 0, Q0, Q0 bar, and 1.
I mean the multiplexers, aren't they 4 to 1?
Sorry, I didn't get your point. For D2, yeah?
The multiplexer, is it 4 to 1 or 2 to 1?
Oh, sorry, 4 to 1, yeah. It's 4 inputs, yeah. 4 to 1, yeah. 2-level implementation, yeah. So it's 4 to 1. 0, Q0, Q0 bar, and 1. And then, of course, here we can have Q1 and Q2. Those 2 multiplexers will replace those 2 here by just doing these connections, bringing Q0 here, bringing Q0 bar here, and Q1 and Q2 here. That's it. So this is the last question. So I'll put extra practice problems for you to solve. I'll put as well questions for the revision for the final exam. So try to practice as much as you can. We are done. So hopefully next session we can start from solving some questions from the revision. And then that's it. If you have questions, you can ask. Even questions related to the project, you can as well. Right, no questions. So then that's it for today. Talk to you next session inshallah. Assalamu alaikum.